Neither the life of an individual nor the history of society can be understood without understanding both. In other words, to understand society, it's important to understand the individuals. There are three types of quantitative models in sociology: statistical regression, analytical equations, like in economics, and agent-based models. Statistical regression models are not able to model individuals. Analytical equations can model individuals, however all the individuals have to be the same, and the system has to be in equilibrium. The strength of agent-based models is that they're made for just that, modeling heterogeneous individuals in dynamic non-equilibrium states. They are, however, often not very accurate. Yet. Agent-based models are simulations of agents such as humans or companies. They have widely been used in sociology to gain an understanding of many mechanisms, such as reciprocity, commitment, reputation, and collective behavior. The main criticism of agent-based models, however, is that they're not very accurate, specifically that they're based on manually created rules with manually chosen parameter values. There have been two solutions to this criticism. One, you manually test different parameter values until the simulation looks good. The disadvantage of this approach is that it's manual and vague. Or two, you get the parameter values from empirical observations by first doing a statistical analysis on appropriate data. This is a fantastic approach. It, however, requires there to be good, appropriate datasets to be available, which is rarely the case. I would like to propose a third solution: approximate Bayesian computation for parameterized agent-based models. I will present this new method by showcasing the online platform Tree of Knowledge. Tree of Knowledge automatically learns agent behavior from many different datasets. www.treeofknowledge.ai is an online platform for collaborative agent-based modeling. Users work together to create agents and specify their attributes and behavior rules. These agents can then be used to create a large variety of different simulations. One thing that is new with Tree of Knowledge is that you can create parametric behavior rules, i.e., if you're not certain about some details of a behavior, you can simply create a parameter for the value you're not certain about. The platform then learns these parameter values from data. Let's look at a practical example. Suppose we wanted to analyze the browsing behavior of visitors to a website, and we have their clickstream data. First, we upload the clickstream data to Tree of Knowledge. Next, we add new rules to the agent for any behaviors which have not yet been modeled by other users. In this case, we create the new rule: if the agent is currently on the landing page, then with probability θ3, go to the About page. Finally, we use the agent to model the underlying system. But what does it mean to model the underlying system? Let's look at this clickstream data. We can see that the user was first on page 4, then page 3, then 5. I believe that all data are in fact observations of an underlying real-world system. In this case, the real-world system that produced the data is someone browsing the internet. So, to automatically learn parameter values from data, we have to make a digital twin of this real-world system. The platform will run this digital twin many times with different parameter values to see which parameter value produces the most accurate simulation. For this simulation at the top, the probability of going to the About page, θ3, was chosen to be 0.71. The simulation below was run with the value 0.26. As we can see here, the different parameter values cause the simulations to unfold differently. The accuracy of a simulation is determined by comparing the data produced by the simulation with the data from the real system. Let's call the parameters that produced accurate simulations to be good parameters. We collect these good parameters. The histogram of these good parameter values then gives us the posterior distribution of θ3 given the data. It is our new updated knowledge of what the true θ3 is. This method of Bayesian inference is called approximate Bayesian computation. It's mostly used in biology research, but there are also examples in various other fields. The advantage of learning a probability distribution instead of a single optimum parameter value is that this probability distribution contains the exact quantification of uncertainty. Wider distributions are more uncertain. The advantage of learning a probability distribution instead of a single optimum parameter value is that this probability distribution contains the exact quantification of uncertainty. Wider distributions are more uncertain. Let's look at another example. In this example, we will infer the posterior distribution from multiple different datasets. Let's first create a new behavior rule. The rule here states that if someone is very hungry, then their decisiveness decreases by a yet unknown amount θ4. We would like to infer this amount of hunger-induced drop in decisiveness from data. Now, there are many scenarios where we could imagine hunger and decisiveness playing a role. Shopping in a supermarket and browsing the internet are just two examples that come to mind. Fortunately, we found on the internet datasets relating to these two activities: market basket data and browsing data. For each of these datasets, we do the same as before. We model the underlying system. The platform then automatically finds posterior distributions for θ4 by fitting these models of the underlying system to the real-world data. These two posterior distributions contain the exact learnings from the two datasets. In Bayesian terminology, they represent our updated knowledge of the parameter given the data. It is interesting to note that the decisiveness rule, being part of a bigger model, allows us to do inference even if decisiveness was not directly captured in the dataset and only indirectly influences the observed variables. We can therefore infer from a far wider range of datasets than we could with a traditional statistical analysis. The platform uses Bayesian statistics to combine the two posterior distributions to a new distribution that contains the learning from both datasets. We hope that over time users will add more and more behavior rules to their agents, making their behavior increasingly comprehensive, and that these behavior rules also get increasingly accurate, as their parameters are inferred from an increasing amount of datasets. The advantages of Tree of Knowledge are its ease of use, the ability to create sophisticated simulations by using sophisticated predefined agents and only extending their behavior where necessary, the accuracy of the simulations due to the intensive validation of behavior rules, and the exact quantification of uncertainty. What do I mean with the exact quantification of uncertainty? With Tree of Knowledge, we can not only create agents and infer parameters from them, we can also make predictions, i.e. use the agents to simulate new scenarios. The outcome of such a simulation will, however, not be a single value, but a probability distribution of possible outcomes. This is achieved by a simulation which uses the inferred probability distributions. Effectively, the program samples from the probability distributions and runs a separate simulation for every sample. These simulations will have slightly different outcomes which we can collect and present as a distribution of outcomes. This way, the uncertainties from the parameters' probability distributions are accurately captured in the simulation and its outcome. In fact, as these probability distributions were inferred from datasets, the distribution of outcomes represents exactly our best knowledge of the outcome given the data and the rules. The vision is that with Tree of Knowledge, agent-based models could in future not only be used to make general models of social mechanisms, but also to get an exact quantitative understanding of these social mechanisms, and to possibly one day make reasonably good predictions of social systems. Thank you very much for your attention.